Okay, so in this video we're going to return to simply looking at summation notation and looking at some basic properties of sums written in terms of the summation notation. The reason we want to do this is we want to talk about properties of the definite integral, right? So far we've defined the definite integral, we've looked at a few basic properties of the definite integral. So we looked at a few examples rather of the definite integral, and what we want to do is we want to establish some properties, right? Just as we have properties of the derivative, for example, we have sum rules and constant rules and things like this for derivatives, we want to see if there are any analogous properties for integrals that we can use. Okay, so here are some of the basic summation properties. So one of them is if there's a constant common multiple across all the terms in your sum, you can pull that out of the sum, right? What does property 1 say? If you write this out without the summation notation, this is saying, well, c times a1 plus c times c, just c, plain old c, c times a2 down to c times an can be written as c times a1 plus a2 plus an, right? So this is simply the statement that you can factor out a common multiple if you have one. The second one says that well, the sum of a sum, the sum of a sum is the sum of the sums. How do we want to say this? Well, the sum of AI plus BI is the same thing as doing the sum of AI and then doing the sum of BI and then adding them together, right? So it doesn't matter whether you do the sort of inner summation first, whether you add the terms and then do the sum, or whether you sum each of the sets of terms separately and then add up the results. And again, this is all this is saying is that you can rearrange a sum, right? This is just saying that, well, if I was doing A1 plus B1 and then A2 plus B2 and so on down to AN plus BN, if I'd written up my sum like that, I could gather things up, right? I could gather all the A's and I could write this as, well, A1 plus A2 up to AN, and then I could gather up all the B's and add them up, right? And so this is something that we do all the time. We manipulate sums like this. We know that we can move terms around and add them up in whatever order we want. Okay, the last two are also similarly obvious. This one simply says that, if you go A1 plus A2 up to sum, so you can, basically what it's saying is you could split a sum up into two pieces, right? So you could do that, and that would be the same thing as, so if you added up the first k terms and then you added up the last, from k minus 1 up to n, you added up the remaining terms and then you added the two together, that's the same as just adding everything all up at once, right? The last one is just saying that if you have two sets of terms and everything in one collection is smaller than the corresponding terms in the other collection, then the sum of the smaller objects is going to be less than the sum of the bigger objects. Again, these are all perfectly obvious things, but when you write them down in terms of summation notation, sometimes you have to pause and think for a minute about what they mean. But we'll find that all of these are quite useful when we want to start manipulating integrals using the definition and coming up with some of these properties. Okay. Here are a few special sums. You've seen some of these in action already, right? When we were doing those examples, we saw some of those special sums, right? The sum of, if you add 1 to itself n times, you just get n. Adding, so this is 1 plus 2 plus 3 and so on up to n, right? Here's an easy way to see where this summation formula comes from. I could also write it as n plus n minus 1 plus n minus 2 down to 1, right? I could add them up in descending order rather than ascending order. But then if I kind of, So if I called this sum, if this is my sum, I call it S, right? Well, what happens if I take these and I add them up? Well, I'm going to do 1 plus n, so n plus 1. Again, I can kind of add things in whatever order I want, right? N minus 1, I add 2. Oh, that's an n plus 1. N minus 2, and I add 3. Oh, that's an n plus 1, right? All the way down to, oh, every single one of these is an n plus 1. How many of them are there? There are n of them. N times n plus 1. And what have I really added here? I've added this sum to itself twice. So this is 2 times the sum. So what's the sum? Well, I take n times n plus 1. I divide by 2. These other summation formulas, well, there are some algebraic ways of coming up with them, but they're pretty messy. The way that you normally would establish some of these summation formulas is using a technique called mathematical induction, which is something that you would learn in Math 2000. So you don't have to worry about how to derive these formulas or how to establish that these formulas are in fact true. We're just giving them to you in case you need them for a problem involving a definite integral where you have to calculate the definite integral directly from the definition. Okay, so using some of these summation formulas, we're going to work out some properties of the integral in the next video.